already mentioned what a small world network, small world property means, right? So like when you saw random network and even scale tree network, I said if the average path length between any two vertices in the graph is proportional to the logarithm of n, the number of nodes, is proportional to the logarithm of n, then we can say the network exhibits the small world property. Okay. So the average path length between any two nodes. Okay, so just find the path length between any two nodes and take the average of all of them. And it is proportional to logarithm of the number of nodes. Then the network exhibits small world property. So we are going to see something like a small world network itself. Okay, so what properties or characteristics a small world network should have? That's what we're going to see. So there are a lot of real world networks could be classified under small world networks. For example, the roadmap network, food chain, and several things, different domains. Okay. All right. So let us start seeing what is the property and how to generate them. So. Did I mention what a regular graph is? I think probably. So a regular graph is nothing but every node has the same degree. Okay, so if you look at this graph, each node has a degree of 4. So we can call sometimes also based on the degree, like k regular graph, which means every node has degree k. Okay, so in this case it's a 4 regular graph because every node has a degree 4. Now, what is something characteristic of a regular graph? Every node has the same property as every other node because every node has the same degree because of that. Now, the clustering coefficient is what we're interested at. So, the clustering coefficient is going to be high for the nodes because they're connected to the neighbors. So, you see here, this node is connected to these 4 guys. And then this one has an edge to this one has an edge to this one has an edge to this. So the neighbors are more likely to be connected to each other. So regular networks have this property of having a larger clustering coefficient. Okay. On the other hand, the path length. Okay. So if I want to reach, say, from this node to this node, how many edges I have to go through? I have to go through this, 5 edges. So you have to really kind of cross, at the worst case, half of the network to reach the other side. So regular networks are more likely to have a larger path length between any two nodes. Okay. So they have one good thing, a high clustering coefficient that is desirable because high clustering coefficient is a measure of like what probability that any two neighbors of your node are connected. So that node, which means what? Why high clustering coefficient is desired? Because if that node is removed, the neighbors are still reachable from each other. Okay, so high clustering coefficient is desired from that point of view, but it also has a high path length. Okay, so let me note down things. So it has a high clustering coefficient, then also high path length, a larger path length. Okay. Now, on the other hand, we have seen random networks also in greater detail. So when we saw random networks, what did I mention? The clustering coefficient of the nodes in a random network are going very small, low. Okay, so they have a low clustering coefficient, but they also have a lower path length, which is desirable because you want to have a small world property, reachability between two nodes through fewer edges. Okay. So what we want is to kind of get the best of the both. So we want to have a network that has a high clustering coefficient as well as has a low path length. Okay? So we cannot assume that with a regular network or with a random network. Right? So we want a network that brings in the best of the two. Okay? So what we will do is we'll take up a regular network, okay, and just rewire some of the edges. So what I mean by rewiring, just remove some edges and connect just rewire few edges. Okay, so for example, and we'll see how to decide that and so on. So for example, I disconnect these two vertices and attach this vertex to some other vertex down here or something like here to some other randomly chosen vertex. Okay, so by doing that, what happens? If you just look at these two networks, this is regular network with a very large path length. But because of these fewer links that you just rewired, okay, the path length for this network would have reduced significantly compared to this network. Okay, and with this changes in the few links, we are not reducing the clustering coefficient that much. Okay, so the clustering coefficient is high with the regular network. It would reduce because we rewired some edges, but it's not going to reduce that much. Okay, so the clustering coefficient will reduce a little bit, whereas the path length would have reduced significantly. Okay, so that is the kind of process we're going to go through to generate a small world network from a regular network. So like the names of the model, so for random network we saw it as the Ertos-Renoy model to generate a random network, and then the Barabasi-Albert or Barabasi-Bianconi model for scale-free network. So for generating a small world network, we're going to see a model called the Watts-Strogatz model, okay, after the name of the people who came up with this. Okay, so the rewiring probability is denoted with a symbol called beta. Okay, so if beta is 0, which means what? The probability that any link here is rewired means disconnected and the vertex is connected to somebody else. If it is 0, it means the network will not change. The regular network will stay as it is. Now, if beta is 1, what does it mean? Which means every edge is going to be rewired. So you're going to disconnect the vertices and connect the vertex to some randomly chosen vertex. So basically, you are connecting two vertices randomly, right? So that then after you go through all the rewiring process, the network that you will generate is entirely random network. It's not going to be a small world network. So that's why we have to choose this beta very carefully. It should not be either of the two extreme values. It has to be between 0 and 1. So a lot of people have did some simulations and they found that the beta value has to be very close to 0. Like even with 0.1 as the beta, the probability of rewiring, we could generate a small world network that has very low path length comparable to a random network and still has a reasonably larger clustering coefficient. Okay, is that clear? So that is something people have found through research. So again, sometimes we also talk about the dimensionality of the regular network. So this is a regular network of one dimension. It's like a ring. It's a one-dimensional network. Whereas this is
Sir, can you please go there and the structure? Means after applying WS model, we will get like this.
Right.
Okay, it has less path length and
low path length and still reasonably high clustering coefficient. Because we don't want to reduce the clustering coefficient too much, because this regular network has a very high clustering coefficient. So when you rewire the edges, so what happens? If I remove this edge, some neighbors lose the edges. So, and if you rewire to some other randomly chosen vertex, they need not be neighbors. So the clustering coefficient is more likely to reduce.
Oh, WS model, why we are using WS model? To reduce the path length?
To generate a network in which the path length is lower, at the same time without sacrificing too much of the clustering coefficient. Okay? So Watts-Strogatz model is known for generating small world networks, like how Barabasi-Albert model is known for generating scale-free networks.
Okay. Can you give a simple real-life example for this?
Well, yeah, we are going to see how to generate. Simple real-life example. So you have, say, Well, let me go through the simulation process and then
Okay.
we can talk about where can this be applied. Okay? So you can also do it for what is called this lattice. So it's a 2-dimension. Okay, so you can. So this is a very regular network. You can, as you can see, each node has the same number of neighbors and so on. So you can again rewire few edges and kind of have a small world network like this. So you could think about, like as a real world example, the road networks. So you have, say, a very organized plan in the city with roads like this, okay? But still people find it very difficult to go from one place to some other place because they have to go to a lot of street intersections and so on, okay? So now you may want to build some bridge flyovers or something like that. You know what a flyover is, right? It will go on the top of the roads underneath. So which two roads or street intersections you want to connect such that the average path length between any two nodes is going to reduce. You see what I mean? Okay, so as of this, if this is a regular network of roads like this with nodes representing the street intersections, it's going to take a long time to go from here to here anywhere.
Sir, in GPS also maybe this type of things is happening, right? In GPS, when you will check the roads means distance, yeah, instead of showing the long distance, it will show you the shortest path.
Provided there is a road. So here there is no road at all. So if I want to go from here, this point to this point, what I have to do? I have to go find the shortest path, of course, like this. But
Yeah.
still, it's like 4 street intersections or 4 edges, right? So can I do better than that? Okay, so you want to travel through a fewer number of edges, okay? Or is that clear? So fewer number of stops, like that. Okay, so why people prefer to travel on interstate if you want to go through long distance travel, right? Why can't you go on some smaller road that may be even the same distance, but you have frequent signals, you have to stop. So if you want to make fewer stops, means in this case fewer intersections, you want to, bridge 2 distant nodes. So you can take that as a motivating example. So you want to choose which nodes that you could connect to. Of course, you don't want to rewire the entire network. As I said, that would make it a totally random network. We don't want to do that. So you want to just do few rewiring, okay? And again, we don't really want to even plan that rewiring process. Just for each edge, attach a probability, as we see in the examples, that this edge is going to be rewired. So if that probability is satisfied, then rewire that edge. Otherwise, don't rewire that edge. So if you go through that process, so if beta is lower, you have to rewire only few edges, okay? And you could generate something like this. So now you can see the orange lines or your flyover like kind of thing where you can use those things like the interstate, for example, to go from one node to any other node without really stopping at some intermediate nodes. So the average path length in such network is going to be less. Is that clear? I heard in Japan, I read an article some time back, I'm not sure that it's true. Since Japan is a small country, the land area is smaller, right? So here we have roads only on one layer of roads, isn't it? But there they have like layers and layers of
Because
roads.
of earthquake, they put it like the different shape than others.
No, not only that. So this is a road. So let us say this is a road. Okay, we have only one road. Where in Japan, on the top of it, they have another complete layer of roads, and then another layer of roads, like a building. So they have roads like building.
Yeah.
I don't know whether how much it is true, but I read like an article like that. Okay, I don't know whether I can minimize the distance, but they're covering probably a small land area. Probably too much of traffic with one layer. They're adding multiple layers. So it's something like that. Okay, a ring like a regular network. but probably there will be some interstate kind of thing to minimize long distance travel. Okay, so let us go through an example process to kind of simulate, okay, how to generate a small world network. So we'll start with a simple regular network like this. So it's a ring, okay. So every node has degree 2. Okay, so we want to rewire some of the edges and generate a random network. So what I'll give you is a network like this, a regular graph, and the rewiring probability. Let us assume the rewiring probability is 0.7. Okay, so what we'll do is first write down the links. Okay, so we'll follow our convention of writing the lower ID first, followed by the larger ID. So the links are 1, 2, then 1, 6, then 2, 3, 3, 4, 4, 5, 5, 6. Okay. Now for each of these links, generate a random number. So you all know how to generate random numbers, right? Some use Excel spreadsheet and just generate random numbers. So these are just purely random numbers. Now if the random number that I generate is less than or equal to the rewiring probability, it means we have decided to rewire that link. If the random number that I generate is greater than the rewiring probability, then that link will not be rewired. Okay, so that's the same thing we went through with random numbers before too, right? So which means larger the rewiring probability, the more the chances that you will generate a random number that is less than or equal to that rewiring probability. So if say the rewiring probability is 1, then all the random numbers that you generate are going to be less than or equal to 1. So you basically will rewire every link. On the other hand, if the rewiring probability is 0, then all the random numbers that you're going to generate is going to be greater than 0. So you will not rewire any edge. Is that clear? So like in this case, 0.933 is greater than 0.7. So we will not rewire this edge. We let it stay as it is. Whereas here, like 0.541 is less than 0.7, so we will rewire that edge. So by going through this process, of course, if you generate the random numbers again, you may get different random numbers, so you may decide to rewire some other set of edges. Okay, so it depends on all the random numbers. So again, an exam, if I give you something like this, each one should get different random numbers and should be rewiring different edges.
So I have a question,
Yes.
like random number is automatically like generated,
Yes.
and then if we compare with our probability with beta, then how it will be most of the time will be like good result, like yeah.
Now that's why you are rewiring several, like with a probability. Of course, your graph has several edges, right? So out of 6 links, you are rewiring 3 links.
Yeah.
So that is like what? 1/2, right? And the rewiring probability is 0.7. So it kind of close, not very close, but you see what I mean?
Yeah.
So the rewiring probability is 0.7, which means you would, according to statistics, rewire 70% of the links here. But for the small example, you are rewiring 50% of the links. Is that clear what I mean by that?
Yeah.
So by doing that, you may rewire some 50% of the links. The same set of links may not be rewired by somebody else. But finally, what we want, a lower path length. So we anticipate the path length that you get and the path length the other person gets are going to be almost the same comparatively.
A random number also has like less path length, right?
Random networks has low path length.
Yeah.
Right. So that's what we want to achieve by randomly rewiring the edges. So we decided to rewire them randomly.
Okay, got
So
it.
we are going to try to reduce the path length. Okay? Alright. So let us now start. Yes.
What happens if you get a random number that's equal to the probability?
Equal to means you still choose to rewire.
Still rewire?
Rewire, yes. So let us now start rewiring the edges one by one. So you go one by one. Okay. So let us start with 2, 3. Okay. So what we'll do? So look at the graph. So 2, 3 is the edge that we want to kind of disconnect, and we will decide to connect the first node, which is 2. So 2 is already connected to 1, and we don't want to connect it back to 3. So the candidate nodes to which 2 can be connected is 4, 5, and 6. These are three nodes to which two can be connected to. And we can pick any one of those. So we have an equal probability for one of these three nodes to be connected to. So the probability that 4 will get that link with 2 is 1/3, because there are three nodes. Based on that, each one has equal probability, which is 1/3, 1/3, 1/3. Okay. So this is going to be similar to what